students, now this video discusses about what equates as the relative velocity, where I will be talking about what is the relative motion. We'll be looking at what is the relative velocity. We'll also be able to understand about the Gallilean transformation velocity theorem, and also finally we'll be looking at the relative velocity in one dimension as well as the two dimension. And for you to understand well about this lesson, just have to make sure that you have the full concept about the actual vectors and basically vector resolution, and also the magnitude of the vector given components. And even if we have the system of several vectors in two dimensions, we should be able to understand about how we can come up with the magnitude as well as the direction of the vectors componentry. And that is if we have the system of the vectors. So make sure you have gone through those lessons before you come for this, because those are the basis of this lesson. So in case you are not much about the vector resolution and some other concepts behind the actual vectors, just have to make sure that you have gone through my video playlist on the YouTube channel, and I come across all this thing. Just have to search actually GP Analytical School of Science, actually resolving vectors into components. You'll be able to understand all these things for you to understand what is this video is about. So thank you. Imagine, let's say you are moving, let's say, towards this direction, and say you are moving at a speed, let's say given as, let me have it as, let's say 2 meters per second. Let's say that is the case, and there is someone as well, let's say moving towards the same direction, and let's say is moving at a speed given as, let's say 5 meters per second. Now when you look at this person, what is the velocity, or actually what is the velocity in which this person is moving with respect to you? And when this person looks at you, what is actually his velocity in which he is moving with respect to your velocity? So that's the point of interest on the relative motion. And also think about this. Let's say we have a board. Let's say this is a typical board. Let's say that is the case, and the board is moving towards this direction with a speed, let's say 10 meters per second. And let's say you yourself, you are sitting along the beach. Let's say you are somewhere here. So when you look at the board itself, what is the velocity of the board with respect to you as you are along the beach? And assuming that in the board there is a person. Now when this person looks at you, what is the velocity in which the board is moving with respect to you? And also imagine that you are a passenger in the boat. What is the velocity in which the boat is moving actually with respect to you as a passenger? Now if we say relative motion, that is the movement of object with respect to something else. That is what they call as the relative motion. So it is the movement of object with respect to something. That is what they call as the relative velocity. And for example, it can be, the movement of a car with respect to the pedestrian. It can be the movement of a pedestrian with respect to the airplane moving. It can also be, let's say, movement of, let's say, a body with respect to the flow of water. Can be that. So if we say relative motion, that is the movement of object with respect to something else. And what is that one? We call it as the frames of reference. So frame of reference. We call it as the frame of reference. So which means if we say relative motion, that is the movement of object with respect to the frame of reference. That is what we call it as the relative motion. And the frame of reference can be in a motion or can be at rest. It depends on the case in which you are to look up to. Now how about relative velocity? Now if we say relative velocity, that is the velocity of an object with respect to the frame of reference. That is what we call as the relative velocity. It is the velocity of an object with respect to the frame of reference. Now, if we say the frame of reference, that is the coordinate position of an object. It is said to be the coordinate position of an object. That is what we call as the actual frame of reference. That represents the coordinate position of an object. So which means if we are looking at the, let's say, velocity of a car with respect to the ground, so ground is said to be the frame of reference. That is the coordinate position of an object. Let's say it can be ground, or it can be the coordinate position of a system. We can have an object or the typical system. And the frame of reference can be anything you may tend to compare with respect to as the object is moving. And for example, can be, assuming you are a pedestrian, you can have the frame of reference being a car, like what is the velocity in which you are moving with respect to the car. So which means at that point the car will be regarded as the frame of reference, which is the relative position of an object, or can be a system. So that's how you start to understand about the frame of reference, and also about what we get as the relative motion as well as the relative velocity. Of course, we can also have the relative acceleration, but that's not the part of interest as far as the video is concerned. We'll actually concentrate on what we get as the relative velocity in line with our actual interest. So keep that in mind. Now, how can we be able to express actually a sort of relative velocity? Let's say if we have an object, let's say this is a car, and it is moving towards this direction, and say it is moving with a speed given as, let's say, 5 meters per second. And that is the velocity in which the car is moving with. And let's say we have, this is a pedestrian, let's say seems to be moving towards the same direction. Let's say that is the case. Now, what is the velocity of the car with respect to the pedestrian? Now, the velocity of the car with respect to the pedestrian is expressed as this, and it is laid as the velocity of the car with respect to the pedestrian. So for that case, it means the pedestrian is a frame of reference. And we can also have this as well. If that is the case, it means we can also have the following expressions for the relative velocity. We can also have, let's say, v12 represents the velocity of 1 with respect to 2. And let's say VAB represents the velocity of A with respect to B. Or can be relative to B, can be that. And let's say VC actually B means the velocity of C with respect to B. And what else we can say it about? We can also say, let's say, Vmn represents the velocity of M with respect to N. And also try to come up with the expressions for the following. And also, let's say if we have V52, what is that one? How about VNQ? Let's say VPQ can be that. And let's say VOP, what is that one? And also what is, let's say, VRK. So you should be able to come up with expressions for that, actually, for those actually relative velocity concepts. And let's now be talking about what we call it as the Gallilean transformation. We call it as the Gallilean, transformation velocity theorem. Gallilean transformation velocity theorem. Should be talking about that. So what is the Gallilean transformation velocity theorem is all about? Now, on the Gallilean transformation velocity, actually a theorem, it is basically centered at having, let's say, 3 frames of references. Let's say we have the frame of reference, given as, let's say, we have the ground, and that I'll represent it as, let's say, I'll have to represent it as G. And let's say we have a car, and for that case I'll have to present its frame, or actually I'll have to present it as being given as C. And also let me have, let's say, a passenger, and for this case I'll have to present it as, let's say, B. Now let's see what is all about the Gallilean transformation velocity theorem, if that is the case. Now, Gallilean transformation velocity theorem uses the principle of adding of vectors using the actually rectangular law, and in the sense that, let's say, if we have a rectangle, should be, by the way, we have the triangle. Let's say this is a typical triangle. It is the triangle A, B, let's say C. And for this case, let's say we have something like that. And let's consider the motion of the object from A to C. Now, object moving from A to actually C, there are two ways it has to move. Either can use this direct path, and let's consider the velocity in which the object has to move from A to actually C. We can call it as VAC. That is the velocity from A to C, like that. And also let's consider the velocity he can move from A to B. So the velocity in which the person can move from A to B can be given as VAB, can be that. And from B to C you can also have it as VBC. And at the end of the day, using the principles behind the adding of vector, using using what you call as the triangle, this is the same as having it as, this is the resultant, then we'll have it as, VAC is equal to VAB and plus VBC, like that. So that's how you should have to understand that one. So which means using the triangle law of adding vectors, this is how you should have it. So which means in all cases, as you can see here, we have the velocity, we have the velocity from A to C. Now, if we think of expressing these in terms of the lead velocity, this is how you should have it in the understand about, and that's the basis of the actually Gallilean transformation velocity theorem. Now, if that is the case, then you say velocity of A with respect to C is given as, now what is the frame of reference which is missing here out of the 3 frames of references? So you observe that the frame of reference which is missing here, it is frame of reference B. Now for that case, it will be expressed here, because for this case, what is the first frame of reference? We have it as A. It also be lead here, so that what will come next, it will be the one which is missing. Then from there we'll have what was missing here. Actually, what was being introduced here will be the leading here. Then what is here will be here. What is that? In other words, let me have to present you locally the way I express these things. If we have, let's say, VAB, and basically I text this one as a parental part, and this is the daughter part. Now for this case, this is the daughter part, this is the parental part. Let's say if we have V12, that is, this is the parental part, this is the daughter part. I think that's how you should also have to describe or express much about this. And for the sake of having the good understanding on how you should have to understand that. And for instance, as you can see here, we have the parental part which is A, and we have the daughter part which is actually C. Now for that case, you know, the parental part here also be parental part here, but the daughter part will be the one which is missing here, which is B. Then what is actually a daughter part here will be the parental part here, and what is daughter part here will also be the daughter part there. So that is what we call as the Gallilean transformation velocity theorem. In all cases, that's what it means. And also, let's try to have this. Even if you can have, let's say, let's consider also this other triangle for you to understand, for you to have the, you know, big look on the concept of the relative velocity. Let's say we have that case, and say this is M and P. Let's say that is the case, and we have somewhere like that. So for this case, this is velocity of M with respect to P, velocity of, let's say, M with respect to should be N, and we'll have the velocity of should be N with respect to, we'll have to express it as that. So using the triangle of adding vectors, you know, this would be given as VMP is equal to VMN, and that should be plus VNP. We'll have that as that. As you can see here, you know, the daughter part here should be a parental part here. You know, it is also the parental part here, and the part which is actually the frame of reference which is missing here, it is what is the daughter part here, and what is the daughter part here, it is the parental part here, and what is the daughter part here, it is the daughter part here as well. So that is what we call as the actually Gallilean transformation velocity theorem. That's how you start to understand that one. So which means in all cases, according to the Gallilean transformation velocity theorem, if we have, let's say, 3 frames of references, let's say G, C as well as the P. Now the velocity of, let's say, G with respect to P will be given as what is the parental part here, also be the parental part here. We'll have it as VG. And what is missing here on the 3 frames of references, we have it as C, so we'll have VGC. And we'll have it as plus C. Now, what is the daughter part here, also be the parental part here, we'll have it as V, actually we'll have it as VC. And what is the daughter part here, also be the daughter part here. We'll have it as that. So this is what we call as the Gallilean transformation velocity theorem. And basically, if we have actually 3 frames of references. Likewise, let's say if we have to express about V, let's say VGC. Let's say that is the case, VGC. So what would be that one? So principle remains the same. The daughter part here also be the daughter part here. That would be VG. And what is missing? That is B. And the plus VP should be C. Like that. So that's what we call as the Gallilean transformation velocity theorem. In that way. Let's say we have the 3 frames of references. We have 1, 2, 3. Now what is V12 if that is the case? V12 will be given as V13 and the plus V3 up here should be 2. We'll have it as that. And how about, let's say, if we can have something about, let's say, V23, what is that one? So V23 will be given as V21 and the plus V13. We'll have it as that. And how about, let's say, if we have the following frames of references, try to come up with the following. Let's say if we have N, P, Q. Now what is actually VNP? And what is actually VPQ? And what is actually VNQ if this is the case? And also try to have the Gallilean transformation velocity theory expressions for this. Let's say if we have the frames of references, let's say it should be OP, let's say R. So what is VOP? And what is VPQ? And also what is, let's say, VOR? So if you find this video actually enough, you just have to, don't forget to subscribe to this channel, and for you to keep on being up to date. And also it is a part of, you know, the supporting system, and so that my videos should reach, you know, as far as possible. Thank you. So in this case, that's how you start to understand about the Gallilean transformation in velocity theorem, whereby in all cases, if you have three actual frames of references, you can be able to come up with a different actual expressions based on the way the question comes. So please make sure you understand about the Gallilean transformation velocity theorem. That's the basis of the concept of the relative velocity. Now, let's now have to discuss about relative velocity in one dimension. So what is that one? Relative velocity in one dimension. Of course, from there, we'll also be looking at the analysis of the relative velocity in two dimensions. Let's say if we have the object moving towards this direction, let's say with a speed given as VAB is equal to, let's say, 5 meters per second. And let's say we have another object, let's say being VAC. Let's say that is the case, with, let's say, velocity given as 2 meters per second. So as you can see it here, we have three frames of references involved. We have A, B, as well as the C. Now, what is VBC if this is the case? What is VBC if this is the case? Of course, there is something I didn't specify about. You know, VAB, this is the same as negative VBA, or else V12 is the same as negative V21. Let's say VXY, this is the same as negative VYX. So that's the very important property you should have to understand about the relative actually velocity. So what is VBC? Now, first thing, we should have to come up with the expression according to the Gallilean transformation velocity, in the sense that we have it as VBC will be equal to VBA and plus VAC. We'll have it as that. And what is VBA? Unfortunately, we do not have VBA here. What we have is AB. Therefore, we understand that, you know, VBA is the same as the negative VAB. Therefore, we'll have this one as a negative. So for that case, we'll have it as negative 5 meters per second. And do we have VAC? Yes, we have VAC, which is 2 meters per second. We'll have it as plus 2 meters per second. Hence, we'll have it as negative, 3 meters per second. That is VBC, like that. And how about, let's say, if we have, and since this is actually along x-axis, we can have to present given as, I hat, that is in terms of unity vector notation. And let's say if we have this case as well, let's say we have the object moving with the velocity, let's say Vm given as, let's say, 20 meters per second. And let's say we have another one moving at, let's say, Vnp, let's say about 5 meters per second, like that. So what is the Vmp if this is the case? So first thing, let's come up with the expression. We'll have it as Vmp will be equal to Vmn and plus Vnp, like that. And that we have Vnm, yes, we have it as 20 meters per second. We'll have it as that. and that we have VNP, that is 5 meters. But now since it is going towards the negative direction, we'll have it as a negative 5 meters per second. So that will be given as 15 meters per second, like that. And how about, let's say, now since this is x-axis, we'll have it as I hat in terms of unit vector notation. And let's think of having this one as well. Let's say if we have something about, let's say if you can have, let's say the object having the velocity given, let's say VOP given as 2 meters per second. And of course, let's say if we have something about object moving, let's say VOR with a velocity of, let's say, 6 meters per second. So what is the V actually VPR if this is the case? So VPR will be given as V actually PO and plus VOR, somewhere like that. And of which, what is the VPOR? We do not have. Should be what is the VPO? We do not have, but what we have is VOR. V actually VOP rather. So since VOP is going towards the negative, we'll have it as the negative first. Then since we are looking for the VPO, we'll also have to give the negative towards this. So we'll have another negative as well, negative 2 meters per second. And by the way, this negative is for the fact that it is going towards the negative direction. And this negative, it is because we are to interchange, we are to change or reverse this, and that would be like this. That is in line with actually PO, like that. And what you can have is, we have it as that. And what is the VOR? We have it as plus 6 meters per second. That would be given as 2 meters per second plus 6 meters per second. From there you can have it. And how about the relative velocity in 2 dimension? What is that? Let's say if we have, this is the object moving with a velocity given as VAB, let's say given as 2 meters per second, like that. And let's say we have another object. Let's say it is moving at that with the velocity, let's say AC, somewhere like that, with which is given as, let's say, 5 meters per second. Let's say that is should be per second rather. Now, what is the actually VBC if this is the case? So principle remains the same. We'll come up with the expression that will be given as VBC is equal, VBA and plus VAC, like that. But now since these velocities are in 2 dimensions, then we need to resolve each velocity in components. So let's start with let's start with the first case, that is vector VAB. So we should have to resolve that into components. By the way, we should have to understand that in this case, this is the same as, do we have VAB? By the way, let me just have to leave it like that first. So let's go for the vector VBA first. So what is the vector VBA? Of course, this is the vector, but now we should have to resolve it into components. We have its x component, that is VBAX. And what is the VBAX? Will be the same as 2 meters per second since it is acting horizontally. That is I. Then we'll have VBY, VBAY. We'll have it as 0 because it has no actually y component. We'll we'll have it as that. And go for the other vector, VAC. And also resolve it in the same way. We'll have, VACX. That will be given as 0 meters per second, that is along I direction. And also we'll have VACY will be given as 5 meters per second J, since it is acting vertically but towards the positive direction. We'll have it as that. And therefore we'll have to substitute them here. Now for this case, you should have to understand that we have VAB, but this is not VAB, it is VBA. By the way, we have VBA, but what we have here is VAB. Therefore, we'll have it as negative, that is VBA, and the plus VAC, since we have it as the way it has to be there. Therefore, we'll have to substitute negative. What is vector actually VBA? So VBA has got these components, so which means we just have to simply substitute. We have negative 2 meters. We can just have, let's say we have 2 meters per second, that is along X, and the plus is 0 meters per second, that is along J. And we have, what is VAC? We have it as 0 meters per second, that is along I. That is along I, and the plus, we can have it as, you just have to adjust here. And of which you will have something about, let's say plus 5 meters per second, that is a J component. And from there we'll have to add those actually vectors componentry, where we can have everything in the right order. So have it as vector VBC being given as, so the X components will be brought together. We'll have it as, and by the way, we should have to distribute this negative inside. That will be given as negative 2 meters per second I, and negative 0 meters per second J. And plus, we have it as 0 meters per second I, and plus 5 meters per second J, like that. Therefore, we'll have to bring together all I components. So have it as negative 2 meters per second I plus 0 meters per second I, and like that, plus, then we'll have negative 0 meters per second I, and plus 5 meters, should be J by the way, J like that. And from there what you can have is something about, so we're using the same concept we discussed about resultant vector component, actually using the component method if we have the system of several vectors. So this case we'll have it as negative 2 meters per second I, and plus 5 meters per second actually J. We'll have it as that. Therefore the magnitude of the vector VBC will be given as the square of negative 2 to the power 2 plus 5 to the power 2, and from there you'll be able to have the direction. And by the way, you can complete this one on your own. And the direction is given as the tan inverse of, what is that one? We have it as 5 divided by negative 2. And by the way, this negative has to be put there as well. Then you have the direction in terms of the angle. So that would be the way principle behind relative velocity in 2 dimensions. So it is the same way we discussed about having the result vector using the component method. Just have to go through my video playlist, and of course I'll have to post the link in the comment section below for you to have an access to that lesson for you to appreciate. Let's say if we have this case, let's say we have an object, let's say at an angle of, let's say 30 with respect to the horizontal, and let's say with a velocity of VAB being given let's say 20 meters per second. And let's say we have another object going like this with the velocity, let's say VBC, and at an angle of, let's say at an angle of, should be 10 degrees with respect to the vertical. Let's say given as 5 meters per second, like that. Now for this case, what is actually VAC if this is the case? Now if we think of coming up with expression, we'll have it as VAB, and the plus we'll have it as that and about V actually BC, like that. And from there we'll have to resolve this into components since it's in 2 dimensions. So make sure you understand about vector resolution, and that's the principle we're using here. So let's start with the first one. So let's start with the first one, and we should have to also have it in the same way. So let's start with actually vector VAB. And now vector VAB is given as this, and we need to resolve that into components. And much as you know about the vector resolution, we can think of coming up with the Cartesian plane from the tail of the vector, like that, and I'll have it as being given as that, where this is x component and this is the y component, like that. So what is the x component of the vector, as you can see there? So for this case, what you have to understand is that we'll have something about or have it as this is adjacent and this is hypotenuse. So make sure you understand about the vector resolution. We're just applying here. So in this case, adjacent, hypotenuse. What is that one? We have it as a cos. So therefore we'll have VABY should be x being given as 20 times cos 30. So 20 times cos 30, that will be given as 17.3. And since it is going towards the positive direction, it will be positive. So have it as 17.3 meters per second. And how about this? This is opposite hypotenuse. That is sine. So in this case, we'll have it as VABY being given as, we'll have it as 20 times it should be sine of 30. That will be given as 10. So we'll have it as 10 meters per second. So therefore we have VAB actually x being given as 17.3 meters per second, and VABY will be given as 10 meters per second, like that. Then we should go for the another actually vector and also do it in the same way. And using the same principle, we should also have to resolve this into components. What you can have is from the tail of the vector, we should have to draw the Cartesian plane, sort of. So in this case, we have this actually a triangle. And looking at the direction of the actual vector, then the components has to follow the same direction, but in other ways. We'll have it as that. And now this is x component, and this is y component. So what is the x component? So we have opposite, hypotenuse. That would be sine. So which means we'll have, VBCX will be given as. Now since it is going towards the negative direction, which is this direction, then we'll have to put negative there. So have negative, so negative 5, by the way it's 5 meters per second. We'll have it as, negative 5 times the sine of angle 10. That will be given as negative 0. So negative 0.86 meters per second. And how about the y component? Adjacent hypotenuse, what is that one? Now we have it as cos. Therefore, we can have, VBY should be VBX, should be VBCY will be given as. Now since it is pointing downwards, that is negative direction as well. So have to put negative there. Negative, we have negative, negative 5 times cos of 10 degrees. That you can have it as 4.9. So negative 4.9 meters per second. Now for this case, what you can have to understand is that we have, the vector VBC, the components has actually VBCX, should be VBCX, is given as negative 0.86 meters per second. And how about the y component VBCY? We'll have it as, 4. Should be negative, rather negative 4.9 meters per second. And from there, we should have to add actually these vectors component, the x component and the x component. And by the way, you should have to understand that, as I'm saying, we'll have to add those componentry. But you should also be very careful with the velocities presented on the transformation expression, in the sense that before we substitute or sort of whatever, you can actually so we should have to get that on like that. So in this case, we should have to add these componentry. Then like that, then you have the magnitude as well as the direction. Anyway, you have that and as that. So in your own time, also try to have the following. And also try to have the following cases as well and appreciate. Let's say we have the first case where we have, let's say, VCP given as, let's say, 10 meters per second. And let's say we have another one at an angle 5 degrees with respect to the actually vertical VOP. Let's say the velocity is given as 2 meters per second. So what is the actually should be, what is VCO, if that is the case? That is the direction as well as the magnitude. And also let's have this case as well. let's say if we can have something about, let's say we have this case at an angle of let's say 59 with respect to the actually horizon, and this is Vxy, which is given as let's say 100 meters per second. Let's say we have that one, and say we have another one going like that, which is let's say 15 degrees at an angle. You know, Vmx is given at let's say 20 kilometers per hour. So how do you think we should have to find, let's say, Vmy if that is the case? So make sure you understand about, you know, the velocity in one dimension as well as the two dimension. So you should have to understand that given a typical question, you should have to identify the frames of references, and from there you should have to have the skill on how you can deduce the Gallilean transformation velocity theory expressions. And in case this video is good for you, please don't forget to subscribe. And also the concept behind all this needs you to understand the vectors. So make sure you have gone through much about the concept of the vectors. Basically vectors in one dimension as well as the two dimension. As you can see it here, we're just applying the concept of the vectors. Thank you.